Hello, I am Professor S. Sankaran in the Department of Metallurgical and Materials Engineering. So, the concept of strain, how the strain is defined is linear average strain, that just like just now we have seen that. So, it is always useful to define the strain as a change in linear dimension by the instantaneous value of the dimension rather than this average strain, which is expressed epsilon is equal to integral limits over L naught by LF dl by L, which is equal to ln LF upon L naught. So, this is a natural strain or true strain. So, the change in length also result in change in initial angle between the two lines. So, the angular change in the right angle is known as shear strain. So, the linear dimension what we have looked at for as a deformation can also involve this change in angle. Okay. For example, if you take this square and these two dotted lines makes an angle with respect to this face. So, this shear is measured by the displacement A divided by the H, which is nothing but a tangent, okay, which is nothing but a tangent. The shear strain gamma is equal to the displacement A divided by the distance between the planes H. The ratio A by H, the tangent of the angle through which the element has been rotated. So, the message is the strain need not just be a linear displacement, it can also involve a shear, okay, or change in angles, which is a shear strain. Okay. So, this is again a convention. So, which is shear strain is denoted by gamma is equal to A by H is equal to tan theta. So, having introduced the notations of the stress and strain, we will now focus our idea on description of stress at a point. So, how do we describe the stress at a point? So, this is a cube and which has got the length delta x, delta y and delta z, the height. And you are seeing that there are so many components of the stresses denoted in this cube. So, x, y, z is a Cartesian coordinate, and as I just mentioned in the previous slides, a total stress always it is convenient to resolve into a total stress into normal stress and a shear stress, right. So, you need that is what it is shown in each of this phase. For example, you have this sigma y and sigma x and sigma z. They are all normal stresses, that is they are perpendicular to the plane. Okay. This is a y plane and this is an x plane and this is an z plane. They are normal to this direction and that direction. So, that is they are called normal stress. But if you look at the shear stresses, there are two shear stresses on each plane, like I just mentioned before, two shear stresses. And why there are two subscripts in shear stresses, but in the case of normal stresses only one subscript is given. It is understood that this normal stress act perpendicular to this plane, right. So, sigma y means a normal stress acting perpendicular to this plane y. right here. On the other hand, if you have two shear stresses, you need two subscripts because we need to know first of all where this shear stress lies. So that means the first subscript denotes it lies in the y plane, and the second subscript shows that it is which direction. Right? For example, if you take this tau y z, the shear stress is in the y plane, that is first one, and the direction is x, right. So similarly, you take this is in z plane, but the direction is y. Okay, you take this shear stress, it is in the z plane, so first subscript is z, it is in this x direction, so zx. So you need two subscripts to denote describe a shear stress. This is a mistake, it should be x. So for describing a normal stress, you can denote it by sigma x or sigma y and sigma z and so on. So this is about the description about normal stress and shear stress. But we are talking about description of a stress at a point. So what this diagram suggests is, to describe a stress at a point, you need almost 9 components of stress. That's what it describes. It gives you a clue. Okay. If you are interested in a stress at a point, you need minimum of 9 components, right. So in this geometry, we have taken a cube as a volume element. So 9 quantities must be defined in order to establish the state of stress at a point. By assuming the change in the stress over the phase is negligible due to small size, it can be shown that tau x is equal to tau yx. Thus, the state of stress at a point is completely described by 6 components. So, if you assume this identities, then the 9 becomes 6 components to describe the stress, out of which 3 are normal stresses and 3 are shear stresses, which are sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. Something is wrong there. Yeah. So that is how it is described. So now we are slowly concentrating on description. And we should also know the description of sign convention. So how, for example, if you look at this diagram A, the shear stresses are shown. So, and this type of notation are termed as a positive shear stress. Okay, so you can understand this diagram. It's like this. So you have the element like this, and the shear stress act on this. So it comes like this. So it is forcing like this, and this element will force this. So this way it cycles. So it is counterbalancing both directions, right? So like that. So it is in the positive side. So it is in the positive axis. So similarly, here it is the negative. So shear stress, these notations are useful when you try to do some calculations or describe the state of stress and then try to calculate a transformation of stress. All these things are useful. So these are some of the basics we need to know. So what we are now going to do is, we are interested in finding out a stress at a point. We are going to describe in a 3 dimension. But before we go into 3 dimension, we will first look at them in 2 dimensions or a plane stress. Okay, this is also useful because later we will describe that most of the complicated problems which is being solved with the 2-dimensional assumption, then it is much more simpler to solve. That's called plane stress problem or plane strain problem. But in this case, before we go to 3-dimensional description of stress or looking at a stress tensor, we will start with a state of stress in 2 dimension. Okay, and before we go there, we are also going to consider the stress transformation, right? That means the stress on oblique plane. It is not that we are going to describe a stress at a fixed coordinates or fixed position. So, we would like to look at the stress at a point and it influence, suppose if it changes the orientation from one coordinates to other, how it will have the effect of orientation also has to be accounted for. That is why we take the stress transformation. Okay. So, if you take a stress on an oblique plane, any arbitrary oriented oblique plane, and then how it will worked out to be, including the orientation effect. So, that is what it is going to be described in this. So, before I look at this, let us take this kind of geometry where you have this square which is subjected to biaxial loading. That is why we say that it is a plane stress, right. So, sigma xx, sigma yy and tau xy and tau yx and tau xy yx here. So, this is again a positive shear stress just I showed before, and which is there in the normal Cartesian coordinate x and y. This is a reference coordinates, and suppose if you tilt this whole configuration into some other angle, so then that angle can be theta. So, the x will become x prime and y will become y prime. Then what will happen to this geometry? This also will get rotated. Okay. So, so in order to describe this state of stress, let us consider the wedge. Wedge is this. So, we are going to cut a wedge which is denoted the dotted line here, measured anti-clockwise. This is measured anti-clockwise, because this is what the rotation is. So, it should be anti-clockwise. Let area of face AB is dA. So, AB, this is area line is dA, then the vertical face is dA cos theta. So, we are going to consider this AB. This is an oblique plane. So, if you look at this projection, it is this vertical is this is a vertical face. This is dA cos theta, and an area of the horizontal, this portion is dA sin theta. Okay, so this is an assumptions. So now we will describe them just the wedge portion itself. So that is just a cut and then put it here for convenience. So you can look at the coordinates much more simpler here. So what you are seeing here is this is a new face, and sigma x prime that is double x prime is a normal stress to this oblique plane, and this is the shear stress tau x prime y prime acting on this, and rest all the same. Only thing is what I have just given here is we are interested in look at the force equilibrium in x prime and y prime direction. So, we are looking at this direction and this direction after rotation, right. So, we are going to look at the force equilibrium in this new orientation, and for that we are getting ready with this description like this. So, this is what we have described is dA cos theta is the area of the vertical portion, and dA sin theta is the horizontal area of the horizontal OB and OA. So, the sigma x, this direction multiplied by this area will give the force. That is what it is. So, that is very easy to calculate the force. If you just write it like this, it is easy. So, this is a normal stress and multiplied by area will give the force corresponding to this. Shear stress multiplied by the area give the corresponding force, shear force, normal force, shear force and a normal force, this direction and this direction. But we are interested in this a rotated, an oblique plane, and we are now trying to calculate the force equilibrium based on this particular plane. So, how are you going to do it? So, that is what you have to look at it. So, there is no confusion here. Do not get confused. You can look at this geometry once again. For your convenience, I have put all of them into different color, so that it directly gives the force. So, when you say that the object is in a static equilibrium, then the net force is 0, right. So, that is what we are going to do. Okay. So, again I will bring that geometry for your convenience. So, we are going to look at this total force, net force. We are going to assume that as 0, and then we are going to write that what are all the total force pertaining to this direction, right. We are going to look at this, and this is a convention, sign convention, what we have just talked. So, now let us look at this equation. Sigma x prime dA is a force which is acting on this, that is, this is the normal force I said, and this area is AB plane is dA. So, this is a force that is positive because we are looking at this direction, and minus sigma xx dA cos theta. That means as I said that the projection of this is vertical and this force is negative because you are looking at this direction. So, negative sign sigma xx dA cos theta. Stress into area is a force, but then this additional cos theta comes because of this orientation. We have to take care of that, right. So, sigma x dA cos theta minus this sigma y, this component, which is a negative again because it is this orientation, minus yy dA sin theta, and we are looking at this direction sin theta, and this is again what is xy is again negative, minus tau xy dA cos theta sin theta, and this is minus yx dA sin theta cos theta. So, if you just write this one line equation by looking at this diagram, then everything will be clear. You do not have to worry about it, right. First time, just for your own practice to gain a confidence, you do it of your own and then look at these results, then it is easy, okay. Otherwise, it may look complicated, but look at the geometry first, what are the descriptors, look at them carefully and then try to write of your own, then it is easy. Since I have just typed it here, it may look very simple also, but when you sit and write, you may get confused. So, you try to practice this, then it is easy. So, once you have written this, it is straightforward. After that, everything is very simple steps. So, it is basically rearrangement. Sigma x prime is equal to sigma xx cos squared theta and sigma yy sin squared theta and 2 tau xy sin theta cos theta, and then we have removed dA, which is common for both sides. So, this now a simple trigonometric identity you can just bring in. So, cos squared theta can be replaced with this 1 plus cos 2 theta by 2, and sin squared theta can be replaced by 1 minus cos 2 theta by 2, and sin theta cos theta is replaced by sin 2 theta by 2. So, now we have the equation. So, sigma x prime is equal to sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 and cos 2 theta plus tau xy sin 2 theta, just by rearranging this. Okay, so this is one first equation of normal stress with arbitrary orientation. So if you what does it mean? That means if you want to find out the normal stress in a oblique plane, if you know the theta, plug in the theta values, you will get the normal stress value. So now similarly we are interested in shear stress. So we will look at in the y direction, that means sigma y prime direction, that is tau x prime y prime here. So similarly you just look at all the components here. So here tau x prime y prime dA, this is a force, the shear force in this oblique plane. So that is positive, and now you see plus sigma xx dA cos theta sin theta, because we are looking at this component, this direction, which is this component. So that is positive here, and then minus rest all remaining same here, because this component which is affecting or coming to this direction, minus yy dA sin theta cos theta and minus tau xy dA cos theta cos theta. So rest all the same, this one and this one is the same orientation, but the tau yx dA sin theta and sin theta, which is again changing the direction similar to normal stress. So this is another equation. You have to just look at this geometry and then write, then it is easy. So similar to this, this is got one equation. Then we can replace that or rearrange that with common factors you remove, and then you rewrite this, and final expression can be tau x prime y prime is equal to minus sigma xx minus sigma yy by 2 sin 2 theta plus tau xy cos 2 theta. So this is another shear stress equation. Similar to this normal stress, if you plug in this 2 theta value in an arbitrary plane or member, you will get the shear stress. And similar to sigma x prime, you can also do the same thing for sigma yy. It will also similar expression you will get. So these three equations are the fundamental equations from where we can just build up to find out all type of stresses and orientation effects we can correlate. So this equation, this particular type of derivation is quite useful if you practice by yourself, and we will now just look at some description about this. So the above equations describe the normal stress and a shear stress on any plane through a point in a body subjected to a plane stress situation. So it is a stress transformation in 2D or a description of stress at a point, an oblique plane with with the 2 dimension, whatever you call it, but it is a plane stress situation, right? So we are talking about sigma x and sigma y. It's a plane stress situation. So it is interesting to note this graph and how this, for example, if you look at this similar geometry what I have drawn, suppose if you assume this a biaxial situation, it is here sigma x and sigma y has got some specific values. So in order to appreciate what this graph is showing, so the sigma x is equal to 80 MPa and sigma y is equal to 10 MPa, and the shear stress is minus 10 MPa. So it is plotted on this graph. This is a normal stress or shear stress tau versus the orientation. So all that we have now looked at is how this stress in a 2D will have an effect of theta, that is orientation or transformation, whatever we call it. So this gives a clear demonstration how it looks like. So, what is that we are seeing here? So, the figure shows the variation of normal stress and shear stress with theta for a biaxial plane stress situation given at the top of the figure. So, this is a figure we are referring to. The maximum and minimum values of normal stress on the oblique plane through the point O occurs when the shear stress is 0. So, what does it mean? What are we seeing here? So, shear stress is 0 is here. So, this is where the maximum and minimum values of normal stress on an oblique plane. Okay. So, the maximum and minimum, it happens here. Okay. So, this is 0 and this is 0. That is what it says. Maximum and minimum normal stresses on an oblique plane through point O occur when shear stress is 0. So, shear stress is 0 here and here. Okay. So, the maximum and minimum values of both normal stress and shear stress occur at an angle which are 90 degree apart. So, the maximum and minimum values of both normal and shear stress. So, normal and shear stress maximum and minimum, maximum, minimum, maximum, minimum. The interval is 90 degree, that is what it says. So, the maximum shear stress occurs at an angle halfway between the minimum and minimum normal stresses. So, this is what it is, halfway between the angles, the maximum shear stress halfway between the minimum of normal stresses. This is minimum and should be a maximum normal stresses. So, this is halfway. So, variation of normal stress and shear stress occurs in the form of a sine wave with a period of theta is equal to 180 degree. These relationships are valid for any state of stress. So, this is the sine wave function. So, similarly, you will have a sine wave function of this. Okay. So, the another classification is the planes on which the maximum normal stress act and on which no shear stress act are called principal planes. And the stresses normal to these planes are the principal stresses. So, before we get into the much more detailed definition of this, so let us get into the nomenclature of what is principal plane and principal stresses. So, this is the starting point. Planes on which maximum normal stress act and no shear stress are called principal planes. Okay, something like this situation. Shear stress is 0 here and the normal stress will have a maximum. So, this will happen at particular planes. Those planes are called principal planes, right? And the normal to these planes, they are called principal stresses. So, principal stresses means there is no zero shear stress. So, that is the bottom line we have to remember always. So, since by definition a principal plane contains no shear stress, its angular relationship with respect to the xy coordinate axis can be determined by finding the values of theta in equation 2, for which tau x prime y prime is equal to 0. So, we have now derived some equation which describes the shear stress on a plane stress situation for an oblique plane or arbitrary theta. So, if you, in order to find out the angular relationship, if that equation is being made into 0, then we will be having some relations. We can develop some relation. What is that? This is the relation we have taken from the previous slides. If you look at the shear stress expression, this is the same shear stress expression. Then we are trying to make it equivalent to 0 and then try to rearrange that. So, if you do this, tau x y divided by sigma y minus sigma x minus, because it is a sign reverse here. So, sigma x minus sigma y is equal to sin theta cos theta divided by cos squared theta minus sin squared theta, which can be written as this. Okay. Then this can be written as half tan 2 theta, and this one finally can be written like this: tan 2 theta is equal to 2 tau xy divided by sigma x minus sigma y. Okay. So, this is an angular relationship we are talking about with respect to these stresses. Okay, what is that I am trying to show here? Equation 1. What is equation 1? Equation 1 is sigma xx, what we have derived in this 2D case. If you plug in all the values for cos 2 theta and sin 2 theta, then the values, it will give the principal stresses, right? The equation will give the principal stresses, that is sigma 1 and sigma 2, right? So, how do we find this the value of this? So, we are seeing this. So, what is this? If we can take from this relation, we can simply we can also do this. Suppose if you assume this as a 2 theta, so from this relation you will be able to find out what is this, right, using Pythagoras theorem, right. So you, because of using that relation, so you will be able to find sin 2 theta. So from this equation you put it this, and then this is tan 2 theta is 2 tau xy divided by sigma x minus sigma y will give you a simple Pythagoras relation. You will get this: sin 2 theta is equal to plus or minus tau xy divided by sigma x minus sigma y whole square divided by 4 plus tau square xy to the power half. So, this will be your hypotenuse. So, it comes like this. So, similar equation for cos 2 theta. I am just giving you so that you will be able to appreciate from this relationship. You will be easily able to derive this using simple mathematics and still appreciate the physical concept they are trying to visualize. How do we find this principal stresses in a biaxial situation, right? So, again, from using this, after substituting this, this is the final expression you will get from this the original equation. So, that is sigma max and sigma minimum, sigma 1 and sigma 2 is equal to sigma x plus sigma y by 2 plus or minus sigma x minus sigma y by 2 whole square plus tau square xy whole to the power half. So, this is the expression for maximum and minimum principal stresses for a two-dimensional state of stress. So, what you see here is once you get into the grip of getting the common equation, then it is very easy to plug in the values of theta and then arrive at some expression for principal stress. It may look, the equation look very complicated, but if you just sit and work it out, you will not find it difficult. The most important point is you will get the physical picture. You should keep that physical, the dimensions, everything in mind, and then it will be very easy to grasp this. Okay. Okay. What we can do is now what is this figure? This figure shows a shear stresses, which is a negative shear stress, and this is a shear diagonal, and this sigma s is a normal stress, and sigma y again a normal stress. Suppose if you want to get an idea of how to establish the sigma 1, right? How do we find the sigma 1? This figure shows a simple way to establish the direction of a largest principal stress sigma 1, and sigma 1 will lie between algebraically largest normal stress and a shear diagonal. Okay. You see, when we describe this sigma, I mean the state of stress in a 3 dimension, again we will come to this point. Sigma 1 is the largest principal stress, and then sigma 2 and then sigma 3, right. And the maximum shear stress will occur at 45 here, right, 45 degree. And then when the sigma 1 has 0 shear stress, then it becomes sigma x normal stress, right, that is principal stress. If there is 0 shear stress, it is principal stress, and then it is a pure shear here. To see this intuitively, consider that if there is no shear stresses, then sigma x becomes sigma 1. That is what I am saying. Suppose if you say sigma x does not have a shear stress, then it becomes sigma 1. If only shear stress act on the normal stress, that is principal stress, would exist along the shear. If the principal stress itself a pure shear, then it is only on the diagonal, right. So, if both normal stress and shear stress act on the element, then sigma 1 lies between the influences of these two effects. So, this is a very nice way of looking at it. If both normal and shear stress act on an element, so it has to lie somewhere in between, right. So, because it has got both the components, whether normal, it will be a normal stress here as well as a shear component, right, somewhere. If it is not pure shear, it is not pure principal stresses, but somewhere in between. Okay. If the both normal and shear stress act on an element, then sigma 1 lies between the influences of these two effects. So, that is the effect I wanted to show in this image. So, here again sigma x is greater than sigma y, like sigma 1 is greater than sigma 2, then sigma 3, something like that. So, this image clearly shows the how to visualize sigma 1 or how to visualize the sigma when a body is subjected to both normal stress and shear stress. Okay. I think we will stop here, and we will continue the discussion on this stresses and their derivation in the next class. So, what I would like to tell you before I wind up, so these geometries and the equations, unless you practice of your own, it will be difficult. So, you just go through the slides, because in a PPT it may appear so simple. So, but I am not saying that it is difficult or something, it is elementary only, but the point is you have to practice by yourself. After going through this, you try to practice yourself, then it is easy. Okay. Thank you.